All right, in this video we're going to look at integration in cylindrical coordinates. And so what you're seeing here is a little differential volume element in cylindrical coordinates. And so now for a triple integral, we're going to integrate over some three-dimensional solid. And in rectangular coordinates, we just divided that solid up into a bunch of small little differential boxes whose volumes were dv equal to dx dy dz. And now in cylindrical coordinates, if I vary r a little bit and theta a little bit and z a little bit, we are going to create one of these cheese-shaped wedges for our differential volume. And to compute the volume, first notice that in the base here of our solid, we're looking at one of these polar rectangles. And back in 14.3, we argued that the area of one of these polar rectangles was the length here, this little circular arc, whose length would be r d theta, right? Because if I say that the distance from the z-axis out to this point is r, and then I sweep it through the angle d theta, it would have length r d theta. And then if this is dr, taking the product of these two, there is your area for your polar rectangle. So that's the area of the base of our figure. Now the height is just our small change in z. And so the volume of this wedge would then be the height dz times the area of the base, which is your r dr d theta. And so then to set up a triple integral in cylindrical coordinates, well, just like for double integrals in polar, we're going to replace x with r cosine, y with r sine, z is just z. We're going to have to set up appropriate bounds for z, r, and theta. And then again, for the differential volume element, we're going to have our dz, then you pick up that factor of r, and then dr d theta. Okay, so in the next video, we'll work through question 2 to see all of this in action. Thanks.